Derivative of inverse functions. Now we all know that if you have f of a and if you plugged in some number a and got b, that means for the inverse function, what do you plug in and what do you get? What's the inverse?
Plug in B and
Yeah, so the inverse function switches input and output, right? So if you plug in b, you should be getting a. That's what it means. Okay. Now this is basically the definition of the inverse function. And there's an important corollary that you can get immediately after seeing this. It's that if you compose f with f inverse, if you nested if you nest the f inverse into f, or vice versa, they basically cancel. If you compose f with f inverse, they cancel each other. Now let's see why. Well, let's just plug in b. So suppose you plug in b into f inverse, then you get, because we said f inverse of b is a, you get f of a, right? But what is f of a? B, right? And because a and b were some arbitrary pairs of input and output, right? We chose a arbitrarily and b was its output, right? This should hold for any value b that's in the range of f, okay? Same thing would hold if you had f inverse of f a. What's f of a? That's b, right? So I can replace f of a by b. What's f inverse of b? That's a. In both cases, if you look at the beginning and the end, what effectively did we do? We effectively just cancel the f and f inverse, right? If you cancel these two, you get this, right? If you cancel these, you get that, right? Okay. So, using this, I want to talk about the derivative of an inverse function. So, all this is saying is that if you have f composed with f inverse of x, that's same as x because they cancel. That's what I'm trying to say. Now, my question is, does this have any implication in the derivative of the inverse function? And the answer is yes. Okay? Let's see how we can do this. So the first thing I want to do is I will differentiate both sides. Okay, and let's see what we do. Okay? So I'm going to differentiate both sides. Differentiate the left side, differentiate the right side, and they should still be equal. On the right side, it's easy. What do you get if you differentiate x? It's just 1, right? The left side, you have to use the chain rule, right? What does the chain rule say? F inverse of, no, f prime, you have to differentiate the outside function, f prime of f inverse of x, the inside is untouched, but then the chain rule says this inside function has to be pulled out and be differentiated, right? Okay. Then we can see this as a formula for f inverse. We can see this as a formula for f inverse prime. So the important outcome is that if you have f inverse of x and you differentiate it, that's same as 1 over f prime of f inverse of x plugged in. Okay? Now let's try to use that formula for some specific example. Okay? So the first thing I want to use is we did ln of x, right? we use ln of x, and I said e and ln cancel, right? Why is this true? When does two functions cancel? If they are inverses of each other. Okay? So what is the logarithm? It's the inverse function for the exponential function. Okay? That's how you were introduced to the logarithm when you learned it in pre-calculus. Okay? Although you may forgot about that and completely forgot that any relation between the exponential function and log function existed at all. They are really inverses of each other. Okay? So because this is true, this means that ln of x is really this e to the x. It's the inverse of e to the x. That's what it is. Okay. All right. So therefore, according to this formula, if I want the derivative of ln of x prime, then it should be 1 over e to the x differentiated. You have to differentiate this, and inside the x, you have to plug in ln of x. That's what it means, right? After differentiating f, you have to plug in the inverse function into it. Okay. So, well, what does that mean? That means what's the derivative of e to the x?
E to the x.
And inside x, what should we plug in? ln of x. Now, don't they cancel? Right? So what do we get? 1 over x. So we get that the derivative of log x is 1 over x.